Welcome back to the AICE Chemistry lecture series. We're going to be covering chapters 3, section 2 today, which covers hydrated and anhydrous compounds. Now, this is a pretty short section, but it's one that's very important because it's going to come into play later on when we talk about gravimetric analysis practicals for paper 3. So once we talk about the stoichiometry and molar masses later on, we'll talk about that practical. But let's get right into hydrated and anhydrous compounds. Hydrated compounds are specifically a type of ionic compound that happen when an ionic crystal forms and it traps water within that crystal. So if you remember from Honors Chemistry, this is what an ionic lattice looks like. Ionic compounds look like this, where you have a repeating set of anions and cations that kind of surround each other. When those ionic compounds form in water, the water molecules can be trapped inside of that lattice. We call this a hydrated compound. And it's essentially just a compound which contains a definite number of moles of water in their structure. Now, this is very important. It's not just any random amount of water. When a hydrated compound forms and the water molecules are trapped within the crystal structure, due to the shape of the crystal structure of different compounds, they will have different amounts of water trapped in them. And it's always the same amount. And we'll get into that in the next slide, but it's not just a random amount that's going to vary from one crystal of one compound to the next crystal of the same compound. It's always going to be a definite amount, a specific number. And we can see here what these look like, because one of the common misconceptions about hydrated compounds is that they're wet or that they're liquid. They're not. Hydrated compounds are solid compounds. Here we have an example of hydrated cobalt-2 chloride. Cobalt-2 chloride is this beautiful crimson solid crystal. And so we can see here that it's not liquid, it's not wet, it's just a solid compound. In the crystals, though, there is water molecules, not a large amount of water, but water molecules trapped within that crystal. The opposite of a hydrated compound is an anhydrous compound. And the name kind of defines itself. An anhydrous compound is a compound which contains no water of crystallization. So these are compounds that had either been dried up or that when they formed, they did not trap water in their structure. This is anhydrous cobalt-2 chloride. So this is the anhydrous version of this hydrated CuCl2. You can tell by looking at the pictures that when a compound is hydrated, it can actually change its visual appearance and its color. Anhydrous cobalt-2 chloride, is this nice, beautiful blue color, whereas hydrated cobalt-2 chloride is this nice crimson color. So they're the same exact compound. This is still CuCl2 in both cases, but the presence of those water molecules trapped in the crystals changes how this compound interacts with light and therefore changes the color of the compound itself. But the only difference between these two is that one, the anhydrous does not have water trapped in the lattice. The hydrated does have water trapped in the lattice. So, the water of crystallization. We can show what we call the water of crystallization of a compound by using a dot followed by the number of moles of water in the chemical formula for that compound. Now, what are we talking about here? We're talking about the water trapped in that ionic lattice, because when a hydrated compound forms, they don't do so sporadically or randomly. When an ionic compound forms, that crystal lattice has such a shape, such a structure, that it's always going to trap the same amount of water. So for example, copper-2 sulfate here. When copper-2 sulfate forms and it traps water in the lattice to make hydrated copper-2 sulfate, it's always going to trap 5 moles of water for every 1 mole of copper-2 sulfate. We call that the water of crystallization. The water crystallization is a specific number of moles of water associated with a mole of the crystal structure. And this is not changed. These are always the same. So copper 2 sulfate, when it forms, it will always form by trapping 5 moles of water for every 1 mole of copper 2 sulfate lattice. Now, different compounds may have a different level of water of crystallization. Copper 2 sulfate, as we see here, has a water of crystallization of 5, but the cobalt 2 chloride that we saw earlier on in the other slide has a water of crystallization of 2. 2 moles of water for every 1 mole of the cobalt 2 chloride. But with copper 2 sulfate, it's 5 moles of water. That's going to depend, and there's no actual way of figuring out what this number is other than experimentally. It's actually the topic of one of our practicals. The gravimetric analysis practical that we're going to do later on is going to use a heating element by dehydrating a hydrated compound and turning it back into an anhydrous compound to figure out what this ratio between the ionic lattice or the ionic compound is and the water to figure out the water of crystallization. Now, the hydrated compound having that water in there, having that water crystallization number, will affect a few things. Now, one of them we already talked about, which is that it may affect the color of the compound. It may or may not. With cobalt 2 chloride, we saw how it changes the color from blue to red when it's from anhydrous to hydrated. With copper 2 sulfate anhydrous is actually white, but when it's hydrated with water, it actually turns blue. Now, that's one thing, and that may or may not happen. But what will always change when we have a hydrated compound, as opposed to the anhydrous compound, is the relative formula mass. What you have to realize is that when we have a hydrated compound, the water trapped in the lattice becomes part of that lattice. And so when we're talking about the relative formula mass of anhydrous copper 2 sulfate, that's simply just 159.62 AMUs. We add up the atomic masses of 4 oxygens, 1 sulfur, and 1 copper. But if we're talking about the relative formula mass of hydrated copper 2 sulfate, that's now different. Because those 5 water molecules, or 5 moles of water molecules, trapped inside of the lattice add mass, add weight to the lattice. So the relative formula mass of a anhydrous copper 2 sulfate or an anhydrous ionic compound, and the relative formula mass of the hydrated copper 2 sulfate or an ionic compound are different. When we look at this, if we look at the relative formula mass of hydrated copper 2 sulfate, that is 149.72. Why? Because we have to grab the relative atomic mass of the anhydrous compound, the 159.62, and to it we have to add the mass of 5 water molecules, the relative molecular mass of 5 water molecules. So to that 159.62, we're going to add 5 times 18.02, which is a relative molecular mass of water, to get that 249.72. Again, when we do relative formula mass of an ionic compound that's hydrated, we need to include the mass of that water. And that's very important because it will end up messing up calculations in the future if you don't account for those water molecules in there. All right. That is it for section 2 of chapter 3. We will see you all for the next video, which will cover section 3 of chapter